Hi, everybody. Welcome to another session of Discrete Optimization Talks. Thank you for joining us. We have two wonderful speakers today, Yiling Zhang and Andrew Trapp. We start with Yiling. She is an assistant professor in the Department of Industrial and Systems Engineering at the University of Minnesota. She received her PhD from IOE at the University of Michigan. Her research interests include stochastic programming, integer programming, nonlinear programming, optimization techniques, and statistical analysis. She's been published in various journals such as Operations Research, MSUM, SciEM Journal on Optimization, and she's been recognized with several awards, such as the Honorable Mention for the Optimization Society from Inform Student Paper Prize, the IISc Pritzker Doctoral Dissertation Award, second place, and the Richard and Eleanor Towner Prize for the distinguished academic achievement. With that, please, Yiling, take it away. It's your turn to present your work.
Yeah, thank you, Alexander, for the introduction. I'm really sorry. I tried to use a new PDF reader today, but somehow, when I start sharing, it didn't work. So yeah, so this work is a joint work with Jing Dong from Oak Ridge National Lab. And this is a still ongoing work. So I'm very happy if you have any suggestions or comment on this work. I will first start with the background of the building load control problem. And then I will introduce the distributionally robust chance constraint model for this problem under two ambiguity sets. So usually the risk level of the chance constraint is viewed as a predetermined parameter, but we'll talk about an adjustable variable where this risk level is be viewed as a decision variable, and then comes with some computational experiments. So the problem is motivated by the imbalance issues between electrical supply and demand, which can lead to reliability and resiliency issues of the power grid. So recent years, there is more and more renewable energy sources. So according to the Department of Energy, by the year 2040, there expect to be 29% of total electricity generation from renewable energy sources. So the higher penetration of renewable energy sources can increase the imbalance issues, because generally this renewable energy, they cannot adjust their output according to the changes from the demand side or from the power grid. They cannot provide a consistent and predictable output. So one solution is to use pure energy storage to compensate those fluctuations. But economically, this may not be a wise solution because it requires a huge capital investment and maintenance cost. Then what else can we do to elevate this imbalance issues? So let's first look at the demand side. So this is a bar chart of the US electricity consumption by sector. We can see almost 3/4 of the electricity consumption is from our building operations. So every year there is about $410 billion spent on building operations. So what are these building operations? They include heating, cooling, lighting, appliances, and equipment within the buildings. So traditionally, all these building loads, they act autonomously without any coordination of the changes from the power grid. But recent years, with advanced development of smart sensoring and metering and even control technology, so this building load, they can be grid responsive. So in other words, they can be viewed as virtual storage resources, which can be used to as storage virtual storage devices for the renewable supplies. So for the building owners, this virtual storage resources generate some new value streams because of more efficient use of electricity. So research has shown that by only 8% reduction of water heating and air conditioning, which still maintain the customer comfort and service quality, can result in 10 to 40% savings on customers' bills. For the power grid, with this virtual storage, they require less electrical storage and lower integration cost. So it's estimated $30 billion savings per year of those avoided grid investment. So we can say this flexible building load can be considered as a solution to compensate those fluctuating renewable energy. So to be more specific, we focus on this subset of building operations of HVAC systems. So they are heating, ventilating, and air conditioning. They consist of 44%, almost the half of all the building operations. The main purpose of this system is to provide thermal comfort and acceptable indoor air quality. So the overall target of this work is to coordinate HVAC unit to track or to consume all the solar PV power generation locally while maintaining the thermal comfort. So to be more specific, the problem we consider here, we have NS HVAC units. And for each HVAC unit, we need to decide whether we turn on or turn off the system. So when we turn the system on, there happens a PG electricity consumption of the systems. And there is a state variable associated with each system, which is the indoor temperature. So the indoor temperature is a function of the binary decision variable UJ. And it's also a function of outdoor temperature, initial indoor temperature, and solar irradiance. So all the parameters of this function is known to us. So this is a linear function of our binary decision variable. The objective here is to minimize the total cost of temperature difference from the reference temperature xref. And also we want to minimize the total number of switch times. So in this model, we consider random solar PV generation, and we assume we know the probability distribution of the PV generation perfectly. Therefore, we can employ a chance constraint to ensure the probability of consuming solar PV generation by all the HVAC units with at least 1 month alpha probability. So this summation is total HVAC load. And the right-hand side is the solar PV generation. So if the HVAC load is larger than the PV generation, meaning that all the PV generation can be consumed locally without sending back to the power grid. And the last constraint here ensure the indoor temperature is within a temperature comfort band. So here is one example of this comfort band. So for this stochastic chance constraint model, we can see we need full information of the probability distribution for the solar PV generation. But in practice, this may not always be accessible. So we may not know the exact probability distribution. So instead, we consider a plausible probability distribution, and we denote this as the set D. So now we want to ensure the chance constraint for any probability distribution within this ambiguity set. So in other words, for any probability distribution, the worst case probability of satisfying this constraint is at least 1 minus alpha. So in this problem, we can see there's a nonlinear term in the object value, but this can be linearized easily by introducing an auxiliary variable. Then if we are able to find a tractable reformulation of this DR chance constraint, then we can solve this model very efficiently. So from now on, I'll focus on this DR chance constraint. So this DR chance constraint involves binary decision variables. And the uncertainty only appears on the right-hand side. So all the results I derived later can also apply to any other individual binary chance constraint with right-hand side uncertainty. So before getting into those, we need to first answer the question, what the uncertainty set we consider here. So we consider two ambiguity set. One is a moment-based ambiguity set. So based on the sample data, we can calculate the empirical mean and empirical occurrence matrix. But when we do not have sufficient data, the moment estimator may not be accurate. So we can allow some ambiguity around this two estimator. So this is captured by the two parameters of the moment-based ambiguity set. So for this ambiguity set, the true mean lies in an ellipsoid centered at this empirical mean, bounded above by gamma 1. And the true occurrence matrix is bounded above by gamma 2 and the occurrence matrix sigma. So we can see if we select larger values for gamma 1, gamma 2, then more ambiguity we allow for the two moment estimator, meaning that we are not confident about the two estimator. And the second set we consider is Wasserstein ambiguity set. So we can generate the empirical distribution based on the n samples. So the Wasserstein ambiguity set considers all probability distribution within a ball centered at this empirical distribution with radius delta. So delta is a positive value. And here we consider one Wasserstein distance. So for a special case, if we let delta to be 0, we can see this set contains a singulator, which is an empirical distribution. Now, let's first see what we can do if we consider moment-based ambiguity set. So for this one, we have an immediate linear reformulation according to our previous result. So here we require the left-hand side to be greater or equal than the empirical mean plus a coefficient multiplied with the empirical standard deviation. So this coefficient omega can be decided before solving the problem. It depends on the relationship of all the gammas and alpha. So we can replace the DR chance constraint with this linear constraint. Therefore, we have an MILP reformulation for the DR chance constraint model. Next, let's see the Wasserstein ambiguity set. So for this one, Chen et al. And Shi already showed that this DR chance constraint is equivalent to the set of nonlinear constraint. So here we have an auxiliary variable gamma and the n for each sample n. So this nonlinear set of constraint admits a conditional value at risk interpretation. So if you divided alpha is a risk level here, right? If you divided alpha on both sides of the inequality, you can see this immediately. So here the nonlinearity is only from this max operation, right? So one very intuitive way to tackle this nonlinearity is to introduce big M notation, and then we have a binary decision variable yn. So if yn equals to 1, so we can say we have this as the larger value for the max operation. If yn equals to 0, then 0 is a larger value. So by the simple trick, we can see we have a MILP reformulation for the DR chance constraint model on the Wasserstein ambiguity set. But this reformulation has n binary variables. So n is a sample size here. So if we have larger sample size, we can see this can be computationally challenging. Then next, we have an alternative MILP reformulation with alpha n plus 1 binary variables. So recall alpha is a small value between 0 and 1. So we can choose like 5% or 10%. So if we choose alpha to be very small, then we can see this reformulation has much fewer binary variables than the previous one. So before showing the results, let's first load all n samples in a decreasing order, and we obtain the permutation of the index. And we further denote PPV0 as the summation of PL. So this is a total HVAC load we have when we turn on all the units. So this assumption says that when we turn on all the HVAC units, the total load should be at least larger than the smallest sample solar PV generation. So this is a very mild assumption. Under this assumption, we can have this mixed integer linear constraints, which are equivalent to the DRCC constraint. So here we have k plus 1 binary variables. So k is between alpha n minus 1 and alpha n. So I know this looks very complicated, but I think this can be kind of easier to understand if I first introduce the proof idea. So let's first start with this set of nonlinear constraints I mentioned before. So for notation simplicity, I denote this max operation using an here. So we know that if we can find Zn and gamma feasible for this set of constraint, then the DRCC constraint is satisfied. So alternatively, we can also view the left-hand side of this constraint as an objective, and all other constraints describe a feasible region. So if we solve this minimization problem, the optimal value of this problem is less or equal than negative delta, then we know the DRCC constraint is feasible. So for this minimization problem, the decision variables are gamma and Vn, and this is actually a linear minimization problem for all these decision variables. So we know strong duality holds. Then if we take a dupe, then the optimal value of the dupe problem is less or equal than negative delta. Then we know DRCC constraint is feasible, right? So the reason we want to consider the dupe problem is because we are able to derive the optimal solution to the dupe problem very efficiently. So for this dupe problem, this can be viewed as a relaxed knapsack problem. So it can be solved efficiently by the greedy algorithm. So we need to order the coefficient of pi n in the objective in an increasing order, and then we allocate the weight to pi n starting from the first element. So for the order of an, because we only have the right-hand side uncertainty. So if we're giving a solution of u here, we can say the first summation here is fixed to us. So the order of an actually depends on the order of PPVN. So recall previously we have this permutation which gives us a decreasing order of PPVN, right? So this is an increasing order of AN. Then based on this order, we have this optimal solution for pi n. And then let's recall what we want to have here is the objective value of this pi n is less or equal than negative delta, right? So before further proceeding, let's recall this permutation we have in a decreasing order, and this is a notation of an. So this is a increasing order for an. So if we assume PPV1 is larger than this summation, then we can say A1 equals to 0, right? So then the value for an should be, for the first few an, we have 0. And starting from some index, we start having positive an. So let's first denote this critical index as J. So this is the first positive value we have for an. And now let's look at the summation. So for this summation, we can say for the first few first the J minus 1, the product is 0 because AN is 0. Therefore, the summation from 1 to n can be rewritten as the summation starting from J. And then we can see for the optimal solution of pi n, the last m minus k minus 1 elements are all 0, right? So therefore, the summation over n product can be viewed as the summation over from j to k plus 1 here. But we can see we actually don't know this critical index j, because this critical index j depending on the solution of u here. So we assign a binary variable xn. So if j equals to n, then this binary variable equals to 1. Otherwise, it equals to 0. So with introduction of this binary variable, we can derive the MILP constraints shown before. And now we can see why we only have like k plus 1 binary variables, because we must have j less or equal than k plus 1, because if j is larger than k plus 1, then we know this summation is 0, because delta is the radius, right? So 0 cannot be less or equal than a negative number. So that's a key idea of this proof. And next we consider an adjustable variant. So here, alpha is not a predetermined parameter anymore. It's a decision variable, and then we penalize it in the objective. So for this model, it can help the decision maker to have a more intuitive idea about the trade-off between the risk level and the cost. So for this model, we also consider the 2 ambiguity sets. Under the moment-based ambiguity set, this problem can be reformulated into 2 second-order cone programs under 2 conditions. So to solve the adjustable trans-constraint model, we need to solve the 2 SOCP, and then we choose the one with smaller optimal value as the optimal solution. And for the versatile ambiguity set case, we also have 2 reformulations. If we based on the MILP1 reformulation for the non-adjustable case, then we can have a MILP reformulation with big M constant. But if we utilize the right-hand side uncertainty as we mentioned before, then we can have a big M reformulation, a big M free reformulation. So here is a case study. We have like 100 identical buildings or HVAC units and 1 central coordinator. And we consider 53 time periods of the daytime from morning to the afternoon. So this is the time when we have sufficient sunlight to generate solar PV output. So the problem we talked before is for a single time period. So to solve this 53 time periods, we need to solve 53 control problems sequentially. So for the first time period, we need the initial room temperature at 820. And then we solve the problem. It can give us a resulting room temperature. And then we use this resulting room temperature as initial room temperature for the next period. So this is how we solve the 53 period problem. We consider 3 models: the trans-constraint model, DRCC on the moment-based ambiguity side, and DRCC on the Wasserstein ambiguity side. So for DRCCW, we consider the 2 reformulation we derived. So we consider 2 typical days. So this is the PV output data for a sunny day, and this is the PV output data for a cloudy day. We generate in-sample data by adding uniformly distributed noise to the nominal value of the output here. And after solving the model, we need to plug the optimal solution in the out sample, in the 1,000 out sample data generated from the same distribution to see the performance of the solution. So let's first compare the computational performance of the two MILP reformulation of DRCCW model. So here we consider different settings of the risk level 1 minus alpha and different settings of the radius of the ambiguity set. So for each setting, we have 5 instances. And we also solve the model using different number of samples. So the CPU time here is the total CPU time of solving all 53 time periods. So for each time period, we have a time limit of 100 seconds. So this column lists the number of time periods which we cannot solve to optimality within the time limit. And this shows the average optimality gap of those time periods. So we can see for all the instances, MILP2 has faster CPU time and smaller gaps. So for example, under this setting, the MILP1 requires 3,000 seconds, and still many periods cannot be solved to optimality. But for MILP2, it requires less than 100 seconds. Almost all of them are solved to optimality, and the optimality gap is much smaller. Next, let's see the tracking performance. So here, after solving the model, we can calculate the total HVAC loads for each time period. So here we have red for DRCCM, green for DRCCW, blue for the trans-constraint model. And the light blue color here is the range of the stochastic solar PV generation. We can see all 3 models track the trend of the solar PV generation very well, both on cloudy day and sunny day and cloudy day. But if we look closer, we can see the red color and blue color are slightly higher. The red and green colors are slightly higher than the blue one. So the DR models provide higher HVAC loads because they consider more ambiguity. So this can also be seen in this indoor room temperature because we turn on more HVAC units. So we can see the DRCCM provides lower indoor temperature than the stochastic trans-constraint model. So next, we want to see the impact of the number of samples on the output sample performance here. So we solve the 3 models using different number of samples. We solve it with 10 samples and solve them with 100 samples. So after obtaining the optimal solution, we plug them in the out samples, and we calculate the percentage of samples where the solar PV generation can be consumed. So that's the probability of locally consuming all PV generation. So here the 10 sample performance are shown in the dotted lines, and 100 sample performance are shown in the solid lines. So we can see for DRCCW, the green color, and the CC model, the blue color. So the solid lines and the dotted lines differ a lot from each other. So which means these 2 models, they are more sensitive to the number of samples. But for DRCCM, we can see they do not differ that much compared to other 2. So DRCCM is less sensitive to the choice of sample size. And we can also observe the similar sense for a higher requirement of the risk level. So in some in summary, we studied the ability of aggregated HVAC loads to absorb solar fluctuations when PV generation is uncertain. We formulate the problem as chance constraint and DRCC models under two ambiguity search. And we develop tractable reformulations for DRCC and DRCC adjustable models. So all the reformulations we derive can also be applied to generate individual binary chance constraint. And then we conduct computational experiments to show the efficiency and effective of the proposed reformulations. So the details can be found online here. And I'm very happy if you have any questions and comments.
Thank you very much, Yiling. Virtual applause from everyone. In the interest of time, we will take questions for you in the breakout rooms that will happen after Andrew's talk. Please, anybody who has any questions for Yiling, stick around and you will have an opportunity to ask her questions at that point. But in the meantime, thank you very much for your presentation, and we'll take it to the next speaker.
Thanks.